Hi Year 8 and welcome to another quick revision video, and this one is all about atoms and molecules in neutralization. It's page 82 in your textbook and it's section 9.3, but for anyone that's tuning in and watching, what I'm going to be talking about are some of the ideas that I really do like in chemistry. It makes us think really deeply about what is actually happening during a neutralization reaction. You would have met neutralization reactions in your high school many times. You may have actually been wondering what is actually really happening. You may have looked at atoms, you may have looked at molecules involved in general chemical reactions, and now in this topic what I'll be going through is how to understand the changes that take place during a neutralization reaction. So first, a quick reminder of some common laboratory acids. We've covered this in the previous video. There are others. There's ethanoic acid as well. There's acetic acid, but hydrochloric acid is the one that is the first one. Please remember capital C, little l. Okay. Nitric acid, HNO3. See where that subscript is at the bottom. That nitrite part is there. The chloride part is there, and sulfuric acid with that little cheeky little F there is H2SO4. That SO4 part over there is the sulfate. But what I need to do is I need you to notice that all of these acids have one particular atom in common, and that is the hydrogen atom. Now, it's an atom within the actual molecule itself, but when it's in water, when it's dissolved in water, that actually becomes separated from all of the other atoms, and not only does it become separated as a free hydrogen particle that makes the solution acidic, it also has a single positive charge. Now, the H in acids can be linked to the scale of pH. In actual fact, we're talking about the term pH. The H, the capital H, actually means hydrogen ions, and this P actually represents the power of the hydrogen ions that are there. The more hydrogen ions there are in a solution, the lower the pH will be. That might not necessarily seem to be very sensible when you start off your studies of acids and alkalis and neutralization, but it's all to do with a mathematical equation that is used to calculate concentration of ions, and it's a scaling factor using a bit of mathematics called logarithms. And that good thing about that is that only comes in A level, and you don't need to worry about that when you're in year 8. But that's pretty much where acids get their acidic property. It's about how freely this hydrogen particle, we call the hydrogen ion, is able to separate out from the rest of the molecule, because if it's tied inside the molecule it can't react, but if it's free it can then go off and react with other things. So hydrogen ions. Now hydrogen ions, well, these are particles, the particles that free up when you add hydrogen chloride as a molecule into water. The particles that free up, well, there are two. One of them is the hydrogen ion, and the second one is the chloride ion. So that's the H, and that becomes H+, and the Cl becomes Cl-. So each hydrogen chloride molecule will split up when it dissolves in water. And just for emphasis, these hydrogen ions are actually shown slightly bigger than I would expect them to be. Okay, it's interesting because it's another lesson altogether as to why it is that these hydrogen ions are actually drawn much larger than the chloride ions. You may think, well, hydrogen is actually a very small ion, but it's also the the power that it has on the water molecules itself. It actually takes around it a whole cage of water molecules. Again, that's a different lesson altogether. But anyway, those are the hydrogen ions that we need to concern ourselves about. So the hydrogen particles here are in actual fact hydrogen ions. They're given the name hydrogen ions because they actually have a charge on them. An ion is a charged particle. The hydrogen ions have a single positive charge, and that's shown by a single positive sign that's just on the top and the right-hand side. It must be on the top and the right-hand side of the capital H that that represents hydrogen in this formula here. So here we have, you may think, well, is this a reaction? It's actually called a dissociation. Dissociation just means splitting. So basically you have a plus and a minus, and the number of positive ions must equal in charge the number of negative ions. So you've got a single plus, a single minus, that actually balances out, and when you add them together, that is the HCl there. Okay, so when hydrochloric acid dissolves in water, we see the dissociation of this acid. The HCl splits to form a H plus and a Cl minus. Now, the hydrogen ion has another name. It actually has the name proton. Now, this is because, and we think back to what we studied before with the structure of the atom, this is because when you actually have a hydrogen atom, and here's a hydrogen atom, you actually have a single proton in the middle of the nucleus and you have an electron on the outside. And so to form the ion, it must lose its single outer electron. And when this happens, all that remains is this single proton that's in the middle. The orbit still there, but the electron is gone. It's like a car that's going around a roundabout, and over here the electron is not there. The roundabout's still there, but the electron is not there. I should note that roundabouts are travelled in the UAE this way, and habitually I went round this way because I'm from the UK, but there you go, that's another lesson altogether. So, we've talked about hydrogen ions being charged particles that are released upon the dissociation of acids in water. And the ion is a H plus because the hydrogen atom loses the single electron to form a nucleus. All right, just a nucleus with a single proton. Now, what we're now going to talk about is alkaline substances. So alkaline substances, in a very similar way, dissociate. So here is sodium hydroxide. It is a very strong alkali, okay, very high pH. When you have sodium hydroxide as a substance dissolved in water, each sodium hydroxide molecule will dissociate when it dissolves in water. The H doesn't come off. The H stays with the O. That's what we find. And the Na does come off. So here are the Nas represented by positive ions, and the OHs are represented by these red circles. That's the O, and the H, which is this part over here. Now that has a single negative charge. Now you'll notice that that has a single negative charge, and the hydrogen ion has a single positive charge. Now, basically, in a nutshell, the H plus will prefer to pair up with an OH minus ion. The OH minus ion is the hydroxide ion. So I'll just show you that dissociation here. NaOH dissociates to form Na plus. Now that stays in the solution. And OH minus, that is called the hydroxide ion. Okay? Right, so metal hydroxides, just like sodium hydroxide, will dissociate very, very readily. So when an acid and a metal hydroxide are combined together, these two equations are very valid. So the first equation comes about because you've got a hydrogen ion from an acid and a hydroxide ion from an alkali. When you add an H plus to an OH minus, the charges balance out and you've got H2O. Can you recognize what that is? It's water. And what's left over now, this is an example where you actually originally started off with hydrogen and chloride, so that was hydrochloric acid, and we're adding that hydrochloric acid to sodium hydroxide, which is an alkali, so the other two ions that are remaining behind can combine together. You can force them to combine together to form NaCl. There's a plus and a minus, and it balances out with both, okay? So NaCl, that's sodium chloride, and that is a salt. So the overall equation for that you have is hydrochloric acid plus sodium hydroxide reacts to form sodium chloride salt plus water. Okay? So this reaction over here will happen whenever you have a neutralization reaction, because neutralization is defined as a reaction that uses up protons like this H+, to form water. Okay? So the general equation for neutralization includes water every single time. The second equation shows how the salt forms from the metal ion and the negative ion in the acid. And that's the basics for the rulings on naming salts. So we can also finally use these two terms over here. And these two terms are terms that you need to understand and be confident with. Proton donors are substances that donate protons. Remember what a proton is? A proton is a hydrogen atom without its outer electron. So any acid that can act like an acid will be a proton donor. Any alkali can accept a proton. Accept means to take on, because they have a source of OH- after they dissociate in solution. So when you have an OH- accepting a proton, we have a substance that can accept protons. So alkalis are classed as proton acceptors. Let's have a look at some of the questions to summarize and test your knowledge and understanding by pausing the video before I go through the question. Why is a hydrogen ion also called a proton? Pause the video. Well, the reason why it's called a proton is because it is only a proton. The hydrogen atom has an electron and a proton, but the charged hydrogen ion is a positive. It has a positive charge because it is just a proton. It's the basic. It's one of the basic subatomic particles that you get to know at key stage 3. What is the charge on the potassium ion in potassium hydroxide, KOH? Pause the video. Now, if OH has a negative charge, the potassium would actually need to balance that out. So the K has a plus charge. It's K+. Why is an acid called a proton donor? Pause the video. So an acid is called a proton donor because in the reactions of acids, we have the acids donating protons to proton acceptors, which are often alkaline. Which ions would you expect to be produced if solutions of sodium hydroxide and potassium hydroxide were combined? Now remember, it's ions. Pause the video. Okay, well the H plus and the Cl minus would come from hydrochloric acid, and K plus, OH minus, remember from the last question, OH minus would be provided by the potassium hydroxide. Right, dissociation equation for sulfuric acid. You will need to consider the charge on the sulfate ion and how to best represent the hydrogen ions that form. So, little clue, the sulfuric acid molecule is H2SO4. So, we actually have 2 hydrogens in sulfuric acid. Pause the video. So what you would actually have is the 2 hydrogen ions coming off, and the sulfate, which is SO4, would remain behind. So your ions that you would have with the dissociation equation would be this. H2SO4 dissociates to form 2H plus SO4 2-. And that 2- would be distributed right across the entire sulfate. So if you wanted to, you could put brackets around the SO4 part. So that would be the best way of representing the hydrogen ions that form. Alternatively, there are some answers that allow you to just lose one of the hydrogens. If you just lost one of the hydrogens, you would have something else that's forming, which is a hydrogen sulfate. And that would be the first stage. That would be the first stage in the dissociation. So that would actually appear like this: H plus HSO4-. However, you do actually find that the HSO4- can further dissociate in a solution, and that can then give you your original SO4 2- that I raised in the first question. Okay, so that's HSO4-, which is called the hydrogen sulfate ion, and that dissociates even further to form H plus SO4 2-. So that's an alternative way of forming. Okay, so year 8, remember you've got the proton. I'm gonna ask you something about proton donors, proton acceptors. Okay, make sure you know your dissociation equations. Okay, and make sure that you can do that for an acid and a base. And don't forget your basic formulas. Remember that 2 hydrogen ions can be donated by sulfuric acid. Best of luck, and do revise. There's one more topic that I need to do in chapter 9, so that's going to be the next video. It's one of my all-time favourite experiments. It's making copper sulfate crystals from copper oxide and sulfuric acid. Okay, and the copper oxide you can actually have formed by the thermal decomposition of copper carbonate. So you heat your copper carbonate, you form copper oxide, and carbon dioxide comes off. Okay, so that's another way of synthesizing it. Love it. Two ways, get some beautiful, beautiful crystals. Hope that's inspiring for you. Take care, revise well, stay safe. Bye.